In this work, we explore efficient and scalable strategies for merging models over time. Before diving into the temporal setting, let's quickly recap model merging more generally. Most prior work assumes we have a base model, we fine-tune it independently of different tasks or domains, resulting in a set of experts, then we merge simultaneously. However, in practice, new domains and applications can emerge sequentially over time, and we often cannot afford to retrain or wait for all the data. That's why we explore how to merge vision language models as new tasks arrive. Let's look at how this temporal setting differs from the standard multitask setup. In the temporal setting, the model is trained on a new slice of data at each time step, and the train checkpoint is saved in a buffer. To systematically explore this setup, we introduce the time framework, short for temporal integration of model expertise. It has three components: initialization, deployment, and the merge technique. The initialization merge happens before training on the current task. Since we have access to all the past checkpoints, we can merge all of them with equal weights, or compute an unrolled exponential moving average. We can also simply continue from the most recent checkpoint, equivalent to standard continual pre-training, or always start fresh with the base model. Deployment occurs after training, when we decide which model to actually use for evaluation or downstream tasks. Similar to initialization, we can aggregate past checkpoints via averaging or EMA, or just deploy the freshly trained model. Of course, it doesn't make sense to deploy the base model. Finally, the merge technique controls how to reconcile the parameters of individual checkpoints into a single model. We use the most popular techniques from the multitask merging literature, such as task arithmetic, ties, lines, etc. What's neat about our framework is that it actually subsumes existing strategies. For example, continual fine-tuning is just last checkpoint initialization and last checkpoint deployment, and standard offline merging is base model initialization and all checkpoints deployment. That means we're not just proposing a new method, we're also offering a unified lens on existing ones. Before we look at results, let's talk about the data. We run all our experiments on the FOMO influx benchmark from our previous work. It contains 2.5 million images across 23,000 concepts, spanning domains like satellite imagery, paintings, medical scans, sketches, and synthetic renders. Each image in the benchmark is paired with a synthetically generated caption, enabling continual pre-training of vision language models like CLIP without requiring additional annotation. For most experiments, we sample a random set of concepts at each task. However, we also verify our results using alternative orderings based on concept frequency, similarity, and dataset origin. Out of the 63 datasets comprising FOMO influx, 41 are used for adaptation, and the remaining 22 are kept for evaluation only. We measure performance using two metrics: knowledge accumulation, which reflects how well the model performs on the adaptation datasets, and zero-shot retention, indicating how well it generalizes to the held-out datasets. Both metrics are an average of accuracy for classification and recall at 5 for retrieval. This plot shows how different combinations of initialization and deployment strategies affect knowledge accumulation and zero-shot retention as new tasks arrive. On the right, we take the geometric mean of the two metrics to get a single performance score. The gray star is the zero-shot baseline, and the gold star is a multitask upper bound where the model is trained jointly on all tasks. I'd like to highlight two takeaways here. First, the choice of initialization and deployment strategy really matters in the temporal setting. Second, there's one strategy in particular that consistently strikes the best balance, namely using an exponential moving average for both initialization and deployment. We call this strategy best in time. Now that we've locked in the best initialization and deployment strategy, we explore the third axis of time. What we found, however, is that once you're using best in time, the specific merge technique doesn't matter much. All methods, whether it's slurp, task arithmetic, or ties, end up performing very similarly. We also test how best in time scales across three axes: model size, compute budget, and task sequence length. On the left, we see that as we increase the model size, Best-in-time consistently matches or even outperforms continual fine-tuning in terms of knowledge accumulation. At the same time, it retains significantly more prior knowledge, improving zero-shot performance relative to the base model. On the right, we increase the compute budget. Best-in-time doesn't just keep up, it actually beats the multitask baseline in terms of retention accumulation trade-off. And finally, though not shown in this plot, we also run experiments with much longer task sequences, 50 and 100 steps respectively. For longer sequences, the performance gap between best-in-time and other initialization and deployment strategies becomes even more pronounced. This highlights its robustness across extended learning horizons. Thank you very much for your attention, and please see our paper for more details.